Hey, welcome back to a new video. My name is Jack Jusko. I am a University of Michigan computer science student who's taking a gap year due to coronavirus related reasons. This video is about using trigonometry in development and specifically in 3D applications. I'm going to go over why trigonometry can be used in 3D applications and give two concrete examples of a situation where you could use it. So, a common criticism of college, high school, and America's education framework as a whole that I've seen both in person, through talking to people, and online is that higher level math, once you get past, say, Algebra 1, Algebra 2, is practically useless. Um, and this is true to some extent. I mean, people make mockeries of using algebra to solve for a Wi-Fi password, etc. But their main point is that there are no real life applications. And in certain fields, certain degrees, this is a true statement. There's a reason why a lot of majors more related to the arts or the humanities will stop requiring mandatory math classes past, say, pre-algebra or calculus AB. Um, and it even often seems true inside more engineering related fields if maybe you're not working with math super frequently, but it still can be used and is still important for doing more complex things regardless of your engineering field. Um, this video is meant to be an example of how trigonometry can be used in a programming field. Um, this video is also on, it's assuming that you have a basic understanding of what trigonometry is, just a high school geometry understanding. I think anything I'll talk about here would have been gone through in maybe freshman year geometry, sophomore year geometry in high school. So it should be something that most people should be able to relate to and relate to any mathematical steps I'm using in this video, more or less regardless of what career path you've chosen. Um, for a brief refresher, common acronym learned in high school trigonometry was SOHCAHTOA. You may not have heard this one, I definitely did. Sine is for the S, then opposite, hypotenuse. So the sine is the opposite over the hypotenuse. Cosine, referred to as cosine, um, is the adjacent over the hypotenuse. T for tangent, or tan, is the opposite over the adjacent. Anything else to know, just as a quick refresher, the sine of an angle x, or theta, realistically, is equal to the opposite over the hypotenuse. The inverse sine, referred to as sine to the power -1 traditionally, of the opposite over the hypotenuse is equal to x, or the angle theta. This is true for all of these operations, with obviously different values for opposite and hypotenuse. So the first scenario I'm going to go over, and I've done both of these scenarios in real 3D development applications, is creating, say, a car that can drive up walls. A lot of game engines have gravity, so this doesn't seem like it's super important. It depends on if you're using a game engine or not to make some kind of racing, driving simulation. Say you have a surface that looks like this. Little too steep there, but that's regardless of the point. And you don't have a built-in gravity engine to work with, so you have to manually figure out how the car is going to drive up and over this hill, and figure out how it is going to change to do this. Now, this is fairly simple at this point. Let's say this is your car, because all you have to do is move it forward. You don't have to deal with any rotations. But once you hit a point like this, this is obviously an unrealistic diagram of how any decent game would look. The car would rotate correctly so that the wheels and that the bottom would be parallel to this ground, so it can successfully drive up this. This would happen in real life. This would happen in any game with the physics engine. But if you need to implement it yourself, this is how it'd be. This would be how to do it. And I'll also talk about this in terms of 3D rotation. So say this is going to be a poor diagram. Say you have a curve like this, where this is meant to represent a lower altitude, and this is meant to represent a higher altitude, like a curve that you would see getting off of a highway or at a skate park. Skate park's a better example, like the side of a bowl, where both horizontal, you need to do rotation in order to fit, say, the skateboard along the inside of the bowl on both horizontal dimensions. So let's say, again, here's your road, your skateboard bowl, etc., where this represents a lower altitude, and this represents a higher altitude. And you need a car, a skateboard, whatever, to be able to remain parallel to whatever point it's over on this ramp for your simulation to work as intended. So here is the bottom of your car as plane 1, call it. And here is the bottom of the road and plane 2, we'll say, where plane 2 is a bigger field and the car is overlapping it in some meaningful way. So we can look at this in 2 different dimensions. Let's look at just if this is 3D attempt coming here. Say this is your X and Z axis, and this is Y, and Y is horizontally. We're not concerned with that at the moment. We're focusing on just hitting a correct X rotation and a correct Z rotation. So first for the X rotation, let's say you are just trying to align it so that you're moving forward in the correct direction. You're not moving into the ramp or above the ramp. So here is your plane 2. This is the horizontal view of plane 2. And say here is your plane 1, where this is a plane, poorly drawn plane, another plane. So 1 is obviously not at a correct angle number 2. It's approaching at too high an angle. It needs to be brought back down to the correct angle. So another term to know before I start this explanation, in geometry, you've heard of a ray. It's a line almost that starts at a fixed point and extends infinitely outward in one direction. It's commonly referred to as R with an arrow over it, or whatever letter it would be. Almost every 3D engine has some way to implement putting a ray and finding the endpoint wherever this ray stops when it hits something, the starting point, and you can use Pythagorean theorem to calculate the distance of the ray. This is something to know for this demonstration. So here's how you could use trigonometry to make this rotate correctly to here. Let's start with the ray that is centered at the bottom of our car, and again, you can do this with any real game engine, provided you just look up the documentation. And we're going to say that the ray is firing, or being pointed, perpendicular. So it's going this way. It's intersecting right here at this point. We'll call B. This is point A. And then say your second ray is pointed directly downwards, towards Z. So it's being fired perpendicularly to plane Z. So we can call the third point point C. So here's our right angle. Here is our hypotenuse, I'll call this h, and we're looking to solve for this angle. Now this angle, which I'll call theta, is the amount of rotation, represents the amount of rotation required to stabilize this car. The way that we know that this angle is the amount of forward rotation required to stabilize the car, let's say here's the second diagram, where here is our plane 1, and here is our plane 2. Here's the first line, here's the second line, and I went over what those represent. And here's the right angle. Now I'm going to draw a third imaginary line here, which is parallel to this first line. Here's the amount of rotation that you can see more clearly that we need to stabilize it parallel to this. We know that since this is parallel, this line is parallel, and this is perpendicular to our plane 2, that this is 90 degrees. So if we're solving for this angle turns into 90 minus x. We also know that since this line is perpendicular to our plane 1, this whole field is 90 degrees. So this field minus this angle turns into 90 minus 90 minus x, the sum of 90 minus 90 minus x, which then simply factors out to x through order of operations. So finding our angle here at this point is basic trigonometry. You can use a variety of different mathematical operations here. Let's say we're using sine. You can use Pythagorean theorem. Once you have different position values in the 3D environment for all three of these points, so you can do sine of angle here is opposite, which is the distance, which I'm going to represent as distance from B to C, over the hypotenuse, distance h. Clear some space here. Clear this too, to be honest. So I'm going to represent distance here as line AB represents the distance from in between A and B. So if we want to find the sine of this angle, it's required for rotation, theta, it's equal to opposite, which is distance AB is distance BC, which is our opposite angle, over our hypotenuse, distance AB. Now to solve for this angle, we can use our inverse sine. So inverse sine of BC over AB will get us our angle. Then you can use your 3D engine to do that rotation and stabilize your car. I'm not going to go through this whole concept again for the second horizontal axis. It is essentially the exact same concept, just looking at it from a different perspective. Now, secondly, I'm sure that many of you have played some game when you were younger where the point of the game is to bounce an object off another object in order to hit a target. I personally played it with a zombie game on the phone maybe 10 years ago, where you bounce a bullet off a ceiling in order to hit the zombie that is standing behind some wall that prevents you from being able to hit the zombie directly. So I'm going to draw this out as a diagram, except for that part. Here is your gameplay field, say your phone screen. Here's where your character is standing. Here is a not so good drawing of a wall that will get the job done for now. And here is your zombie. And say the goal of this game is you shoot a bullet, travels along this imaginary line, because this is the direction you aimed, hits here, bounces off, and you're attempting to hit the zombie. The person playing your game can obviously not see these angles, do them in real time. You need to figure out which point along here, or for whichever point they hit, what angle are you supposed to rebound at, this angle, in order to fire it at the same angle it was approaching. And the goal of the game, realistically, is to figure out where along this line you can shoot it so that it'll ricochet off and hit whatever is standing back here. So now I'm going to go here's an up close look, here's the ceiling. Here is, say, an approaching bullet traveling in this direction. And you need it to bounce off and hit this direction. Very similar problem as before. Say you take a ray, again common in any 3D engine, you fire it perpendicular to the ceiling. You record this point, which is A. We'll say the bullet's point as it's approaching is B. Say the bullet is not quite a bullet. It's more like a rectangular object approaching. You fire another ray parallel to the body of the bullet. You find this is C. We'll use, say, cosine for this one. So cosine of theta is equal to adjacent over hypotenuse. Hypotenuse is equal to distance, BC. You can do that with Pythagorean theorem. Number of other methods. A lot of engines have a built-in way of calculating the distance between 2 points. And our adjacent here, in this case, if we're solving for this angle, is actually distance AC. So now, cosine of theta equals distance AC over distance BC, and then inverse cosine of AC over BC equals theta. That represents this angle here. What we're really trying to find is this larger angle. But say I split this down the middle and I turn this into two 90-degree planes. This angle is represented by 90 minus theta. Again, since these are two almost equal representations, this angle is also theta. Or this angle is also theta, sorry. So this is also represented as 90 minus theta. Combine these and you get the final angle that you need to rotate. So 2 90 minus theta. Now that you have 2 90 minus theta, this is what your final angle is going to be. And you can simply plug in theta for this this expression, and you can rotate that many degrees, radians, whatever you're using, in order to get the correct departure angle for this bullet. That's all I have for today. Thank you for watching. If you liked this video, hit the like button, subscribe, hit that bell at the top. If you didn't like this video as much, but you have different content you would like to see, make sure to drop a comment below. Say what comment that is, if there's something you liked in particular, if there's something in particular you didn't like. Again, leave a comment below. I'll read them. I'll take some feedback, and I'll try to make videos as optimized as possible to what people are looking to learn about. Thanks. Signing off.